Okay, so thank you very much. Great pleasure to be here. The ICTS. I'm greatly enjoyed my second visit to Bangalore, my first visit to this campus. I'm going to tell you about work that is a title that may be unfamiliar to many people. Kelvin's circulation theorem, which I will explain, and how it is related to a picture of the fractional quantum Hall effect, in which a very important role is played by a spin 2 mode, which called a dynamic metric. So the plan of my talk is first to so before starting, I'm going to mention just one fact about the fractional quantum Hall effect, that it is a very non-trivial physical phenomenon that has many facets, and there is no single approach that can encompass all the physics of the fractional quantum Hall. We have the traditional first approach based on the wave function that's pioneered by Laughlin, that leads to investigation of trial wave functions, trial state, and one can see relationship to topology, to conformal field theory, anion, etc., and to topological quantum field theory, another approach that highlights the non-trivial topological excitations in gapped quantum Hall state. And then one of the very fruitful idea was the idea of flux attachment, which one used some rather formal procedure manipulating the wave function and get an effective description of the quantum Hall effect based on some degrees of freedom that we call the composite fermion. I will comment on that picture a little bit later. And there are some approaches that, for the lack of names, I would call that the lowest Landau level approaches. One is pioneered by Shankar and Murthy. There are related approaches by Pasquier, Haldane, Reed, which are somewhat separated from all the approaches that have been I've talked about. And most recently, we have seen a non-trivial relationship between the fractional quantum Hall effect and dualities between different quantum field theories in 2+1 dimension, and a lot of hopes and excitement has been arise through this duality. So to start, let's review the microscopic description of the quantum Hall effect. It's very simple. We start with the Hamiltonian, which is sum of the kinetic energy of n particles in a magnetic field, moving in 2 dimensions only, plus the potential energy, which in this case is just a Coulomb interaction between particles. If we ignore the interactions, the problem is the one that has been solved by Landau in 1930, as mentioned in the previous talks. We have the state of a single particle is organized in Landau levels. And if we have the fractional quantum Hall effect appears when the number of electrons is, for example, smaller than the number of states that can be accommodated on the lowest Landau level. In that case, the problem has 2 energy scales. One energy scale is the distance from one Landau level to another, B divided by M. And another energy scale is the scale of the interaction between the particle on the lowest Landau level. And the non-trivial limit can be taken if we take, for example, M to 0. It's not a limit usually taken in experiments, but it highlights the independence of the 2 energy scale. When M goes to 0, the distance between Landau levels goes to infinity, and all the non-trivial physics happen only on a single Landau level. And the Hamiltonian problem, the problem of this Hamiltonian, can be reformulated in a problem of diagonalizing the potential energy projected to the lowest Landau level. This is the Hamiltonian from which you can see the non-triviality of the fractional quantum Hall effect. roughly speaking, the kinetic energy is now 0, but the potential energy is non-trivial. So the usual hierarchy used in perturbation theory, that the potential energy is small, but the kinetic energy is large, is now reversed. E squared can no longer be used as the small parameter of perturbation theory. We know from experiments that there is a very rich phenomenology of this that arises from this Hamiltonian. For example, from experiment, we know that if the filling fraction, which is the ratio of the number of electrons over the degeneracy of a single Landau level, are of certain fraction, for example, 1/3, the famous 1/3 Laplace state, then we see in its transport the so-called quantum Hall plateaus, which means, theoretically, means that the Hamiltonian that is presented on the previous transparency has a gap. There is a ground state, and the next excited state is separated by a gap, which is finite in the thermodynamic limit. And there seems to be an infinite number of these fractions in an idealized system with no impurities. Some of these are organized into nice series, like n divided by 2n plus 1, n plus 1 divided by 2n plus 1. These are called Jane sequences. And we are going to talk about some physics that happens in these sequences, especially when this number n goes to infinity, large. Now we just keep in mind that these filling fractions correspond to gapped quantum Hall state. Now, picture of the composite fermion was suggested in as one of the possible explanation for the systematics of these quantum Hall plateaus. This n divided by 2n plus 1 state can be thought of as a state formed by a new type of quasi-particle called the composite fermion. The traditional view of the composite fermion is that this is some kind of a bound state or composite object consisting of electrons and a flux quantum. So in this view, an electron absorbs two flux quanta. We attach two flux quanta of the magnetic field to this composite fermions, and the new object is the so-called composite fermions. Recently, one of the drawbacks of this picture has been reconsidered in detail. This picture has been known to be not particle Hall symmetric. The physics on the lowest Landau level has a symmetry when we change particle into holes, while this picture relies on the electrons but not on the holes. The more modern viewpoint on the composite fermions is that it is some kind of a dual fermion that arises when we formulate the theory of electron in a lowest Landau level as a dual theory. The duality here is similar to the particle vortex duality in quantum field theory that has been discovered in the around 1980 by Halperin Dasgupta and by Peskin. But in this case, it is a duality between two fermionic theories. I'm not going to talk in detail about the details of this duality, just I want to highlight some of its features of this dual theory. The composite fermions are in some sense a Dirac massless particle, in the sense that it has a non-trivial pi Beery phase. If I take this composite fermion around a loop that encompasses the point p equal to 0. In this theory, the number of the composite fermion is 1/2 of the number of magnetic flux quanta, and these composite fermion interact with the dynamical gauge field. The magnetic field has an average value, which is equal to the magnetic field, the original magnetic field, minus 2 pi times the number of electrons, so that when the system is near half filling, there is almost a cancellation between these two numbers, and the composite fermions live in a small magnetic field, 0 at half filling. Very importantly, in this picture, the number of electrons is not the same as the number of composite fermions. So this picture of flux attachment, which transforms an electron into a composite fermion, is not something that happens in the strict sense. This number, the number of these two objects do not match exactly, except at half filling. So the duality has solved some problems that has been in existence for at least 20 years in the physics of the composite fermion, namely the problem of particle-hole symmetry. But there are some remaining questions that are always in people's mind when people talk about the quantum Hall effect. It's like elephants in the room. Sometimes specialists do not talk about this, but we also always are concerned about a problem. For example, is there lowest Landau level projection in the effective theory of the composite fermion? The non-trivial effects, the non-trivial things about the quantum Hall effect is that everything can be written in terms of the state on the single Landau level, not the full Hilbert space that matter. It's just a single Landau level. And how does this composite fermion knows that we have taken the projection to the lowest Landau levels? And in particular, does this theory realize the algebra of the projected electron density that known to form a closed algebra called the Germin-McDonald-Platzmann algebra? And another related question is whether the density-density correlator in the theory, where density here is density of the electron, is proportional to q to the fourth. And let me show you why this q to the fourth behavior at small q is related to the fact that we are on the lowest Landau level. So let's consider a theory, general theory with a conserved charge, rho and j. The conservation law of the charge is d rho over dt plus gradient of j is equal to 0. Let's assume that we consider a wave with frequency omega and wave number q. Then in momentum space, this rho is q divided by omega times j. Which means that if I consider correlation function of rho, fixed omega, but taking q to 0, momentum goes to 0, finite frequency, this has to be proportional to q squared. So that's very well-known fact that the two-point correlation function of density due to conservation of charge is proportional to q to the square. But in quantum Hall effect, this is not the whole story, because we have a second conservation law, which is the conservation of momentum. So this is the density of momentum is m times the density of charge in the Galilean invariant theory. And the divergence of this is equal to the Lorentz force acting on the system, J times B, and plus the divergence of the stress tensor. Symbolically, I write as divergence of T. On the lowest Landau level, we can take m going to 0. And the first term disappears. This equation, instead of being a conservation equation, becomes a constraint equation, which relate the current with the divergence of the stress tensor. And we can convince ourselves that means that this J is equal to Q times T divided by B here. Q times T, there are some indices that I have suppressed, but roughly speaking, it's the current itself contains another factor of Q times some physical quantity, which means that on the lowest Landau level, this rho is Q squared times the stress tensor. And its correlation function is Q to the fourth. The fact that this rho correlation function is Q to the fourth is very important in the paper of Gervin, McDonald, and Platzmann. They use that to argue that this gap, they actually derive this from a very different argument based on the fact that the gap has to be finite, Q equal to 0. But this is the I think, the more fundamental reason why this fact is q to the 4th. When people construct theories of the fractional quantum Hall effect, one of the difficult things is to satisfy these constraints. The naive, composite fermion calculation based on RPA approximation, etc., will give you naively this q to the q squared, and that's because I hesitate to say. In numerics, it can be seen. When I say it's q to the 4, it's actually a projected 2-point function. You have to subtract the contribution from outside the transition to the next Landau level. But once it is subtracted, then it's q to the 4. So, and that's q to the 4th behavior of rho correlator can tell us about the spin of the so-called magnetoroton. If we assume, like McDonald, Kelvin, McDonald, and Platzman, that the 2-point functions of, so here there is a typo. I want to say rho correlator, that is rho sandwich between two ground states, is dominated by a single quasi-particle that's called the magnetoroton with momentum q. His rho has momentum q. Then in order for this to be of order q to the 4th, each of these matrix elements has to be q squared. That is, the density operator must have a zero overlap, zero matrix elements between the ground state and the single magnetoroton state. We know that naively, if in a strongly interacting system, a matrix element should not be zero unless there's a reason for it. The matrix element will always differ from zero. So the only reason that one can have here is that this magnetoroton has a spin. If we have a quasi-particle with spin like plus minus n, we are in 2 dimensions, so the spin is just it's just a number. The matrix elements of the scalar operator rho between the vacuum and this q, this state must be from symmetry qx plus minus iqi to the power of n, depending on the sign of the spin of this particle. And in order to have q squared, that magnetoroton must have a spin 2. So in quantum Hall effect, you can see, and I think this argument is first made by Haldane, that the magnetoroton, the first excited state of the system, is a non-trivial spin 2 particle. And Haldane speculated that this, and he has also other supporting arguments, that this particle must, in some sense, be a dynamical graviton. So, so we see here, in some sense, a non-trivial appearance of a quasi-particle that looks like a graviton. So it's, as we will see, it's not a full-fledged graviton like in GR, but in some sense, there are some physics of GR that will be important. So I want to present to you here a view of a composite of a fractional quantum Hall effect that only explains some subsets of the physics of the quantum Hall effect. But on the other hand, it's a very interesting complementary view on the physics. It's based on a picture of the quantum Hall fluid as a real fluid. That is something that can move following the equations of like Navier-Stokes equation, some next iteration of the Navier-Stokes equations. This fluid, in contrast to the usual fluid, has an internal tensor degree of freedom, like a dynamic metric. That's the second point here, very important. And another point that will be important for us, that this particle in this fluid are dipoles with respect to the usual electromagnetic fields. There's neutral fluid, but each of the particle in the fluid, the composite fermion that make up this fluid are electric dipoles. And I will show you that it provides a consistent and rather predictive picture of the long-distance behavior of quantum Hall fluids. It explains some in a nice way, some facts. So let me give you a very short course on hydrodynamics. And this course consists of a single transparency. I've compressed the whole 6th volume of Landau-Lifshitz in one transparency. And it's not a usual treatment that you see in any books. It is, as far as I can tell, it's the treatment of hydrodynamics that was first found by Landau in 1941 in his paper on Bose-Einstein, on superfluid helium. He said that the usual Euler equations of dissipation-less hydrodynamics can be formulated as a Hamiltonian system. The Hamiltonian is a sum of the kinetic energy and the potential energy of the fluid. So the kinetic energy is written in terms of the momentum density, pi, and the particle number density, n. So pi squared divided by 2mn, you can see it's the kinetic energy of a fluid of particle mass m, moving with velocity pi divided by n. So epsilon is internal energy of the fluid. It's the density of energy as a function of the density of particles. So here we assume that the fluid is at 0 temperature. So if one postulates certain commutator or Poisson bracket between this momentum density and the particle number density, we can show that the usual conservation law and the Navier and the Euler equation are just the Hamiltonian evolution of this parameter. So Landau then followed this analogy and built up his theory of the superfluid helium. But we start with this as a starting point, and we want to modify the hydrodynamics by including a new degree of freedom that looks like a metric, dynamical metric that I call Gij. So that is not the external metric that most of the time we are going to put as flat, some kind of a dynamical degree of freedom. And the fact that Gij transform like a tensor can be used to fix the commutator of G with the momentum density. The reason, the physical reason is that the momentum, the total momentum is the translation of the whole system. Density of momentum is infinitesimal transformation. It's like a diffeomorphism. So the transformation of G under diffeomorphism completely fixes the commutator, the Poisson bracket of G with the momentum density. So in order to complete the Poisson algebra, we need to find the commutator of G with G. So here, in 2 dimensions, there is a non-trivial choice that one can make. It's almost a unique choice using the epsilon tensor and G itself. We can show that this choice of the commutator between G and G satisfies all the consistency relation. The most non-trivial of which is the Jacobi identity. So the Jacobi identity, one of these says that the transformation of the left and the right-hand side are the same under diffeomorphism. Moreover, this can give us a way to reduce the number of extra degrees of freedom that we have introduced. So here, if we just take Gij as extra degrees of freedom, then there are 3 independent components. We can consistently actually impose the condition that determinant of G is, square root of determinant of G is the density of particle. And we have introduced into hydrodynamics 2 extra degrees of freedom. And the hydrodynamic equation can be written down if we know the Hamiltonian. And I'm not going to write them down. They are similar to the Navier-Stokes equation, but a little bit longer. S going to be matched to what we will we want in quantum Hall effect. S has to be a constant. Cannot be a function of fields in order for the Jacobi identity to be satisfied. So very roughly, what happened if we write down the equation and try to look at the modes, there is one mode that looks like a disturbance of this metric that I denote here as an ellipse. So this Gij is a symmetric tensor that parameterizes some ellipse, and it's basically rotate in space. The fact that we have used you have broken the reflection symmetry here means that this ellipse can rotate in one dimension, in one direction, and the speed of the rotation is dependent on this coefficient S in the previous transparency and this something called Lamé, I would call some elastic coefficient that tells how the energy of the system depends on the perturbation of the metric. So there is some characteristic frequency of the rotation of that ellipse that tends a degree of freedom. It doesn't stay fixed. It always has a tendency to rotate with a certain frequency. At frequency that is much lower than that frequency, the whole system behaves like it's just a normal fluid, Navier-Stokes fluid, except that there is now a whole viscosity, extra component of the odd component of this viscosity with a value that depends on this parameter S. S times the density divided by 2. And so we can identify S with the average orbital spin of the particles. So what is the relevance of all that to fractional quantum Hall effects? So in fractional quantum Hall effects, one of the picture is a composite fermion Fermi surface. At half filling, that is the ground state. And if one think about the deformation of the Fermi surface, the excitation can be parameterized by the shape of the Fermi surface, which can be thought of as an infinite number of scalar fields. And one can argue that at very low momenta in the regime when VFQ much less than omega, one can limit ourselves to just a few lowest modes. And this GIJ parameterizes the elliptical deformation of the Fermi surface. So if I have a Fermi surface with the shape of an ellipse, then I can parameterize it by its volume, which is the density, its overall displacement of its center from 0, which gives us the total momentum density, and some kind of effective metric that can be written as the second moments of the distribution function of this composite fermion, and give me the shape, this GIJ give me the shape of this ellipse. Like if I constrain my fluctuations only to these fluctuations, then I have a theory that should look like hydrodynamics with density, momentum density, and this metric. Yeah, but maybe I don't have a short way to explain it. But let me maybe I feel a bit later. Just stop at the momentum density. We say that this one, relaxes quickly with the characteristic time scale of the relaxation time, the collision mean free path. So here we have 0 temperature. So in a real Fermi liquid, actually, you have to continue this to infinite number of fields. Only if we are restricted ourselves to a small region in omega and Q spaces. Finite omega over Q actually has to be large, then we can truncate to a finite number of fields. The right thing to do only for restricted, So, for example, this magnetoroton you see in usually it has a minimum. So we have to be far from that minimum. We have to be close to 0. So the commutation relation then can be sort of derived from some semi-classical arguments that I'm not going to tell you here. But I want to tell you that this parameter S, since it's related to the whole viscosity, can be determined almost uniquely by what we know about the quantum Hall state. So for example, we know that it's an average orbital spin of the composite fermion. So based on that and the picture of the nu equal n divided by 2n plus 1 state as an integer quantum Hall state of the composite fermion, we can actually determine this S by just taking an average of what would be the orbital spin of particle on each of these Landau level of the Dirac fermion. To get some number, sorry, I'm going to. So there is one thing that one I have to know is that these composite fermion are electric dipoles with a dipole moment proportional to the momentum and perpendicular to the momentum. And that's going to be important because that means that in the expression for the electron density, there is a contribution that corresponds to the divergence of the dipole moment, which can be written alternatively as the vorticity of the hydrodynamic flow. So if pi over n is interpreted as the velocity of the fluid, this is just the vorticity of the fluid. So the electron density is in some sense related to the vorticity of the, it has a component related to the vorticity of the flow. That brings us to something called the Kelvin circulation theorem. Kelvin circulation theorem is a theorem that has been proven by Kelvin for dissipation-less hydrodynamics in 1869. In 2 dimensions, it just says that the vorticity is in hydrodynamics is conserved, and it's related to the Casimir of the Poisson algebra. Now, in the theory that I have presented to you, there is an extra degree of freedom, and it turns out that this Kelvin circulation theorem can be modified. There exists a generalization in which what is conserved is not the vorticity, but basically the magnetic field plus vorticity plus the Gaussian curvature constructed from this metric. And so one can use another line of argument to identify this curvature with the density of the electron. In the theory that we have presented here, the electron density is not the fluid density, but rather it is the curvature of an auxiliary manifold whose metric is the metric tensor, the dynamical metric of the system. So there is a non-trivial relationship between the physics and the geometry of this Titius manifold. From that, we can show that the density correlator of the electron has to be q to the 4. And it's very easy. The curvature is second derivative of q, and so its correlation function of rho and rho has to be q to the 4. And actually, even the numerical coefficient can be calculated and matched with the prediction from Laplace wave function exactly. And the conclusion of my talk is that there is a theory of the low Q regime of fractional quantum Hall effect in which it's described as a fluid with a dynamic degree of freedom. And the density of electrons that is measured is not the density of the fluid itself, but the curvature of this dynamic metric. And one can do calculation almost algebraically in this theory. Thank you very much. What is the nature?
Landau level?
So it's supposed to describe the physics of electrons on the lowest Landau level, say near half filling. Yeah. But the composite fermions are not the electron. The particle that makes up this fluid is not the electron.
You talked about Hall viscosity. I don't work in this area, but yet you had a Hamiltonian dynamics So what is the, usually if you have a viscosity term in hydrodynamics, I mean, it's difficult to formulate a Hamiltonian dynamics.
So this is a whole viscosity, maybe it's a misnomer, but it's a component in the stress tensor that perpendicular, in some sense, to the stress, and then it doesn't regenerate entropy. So it's dissipation-less.
Comment is the following, that if you take, for example, small oscillations around the Fermi surface, I mean, it's in some models which I've worked with, then there is a full infinite dimensional W infinity algebra associated with it. And if you make a momentum expansion of those generators, then you have particles of all spins actually involved in it. You have made a truncation to the spin 2 particle there. So there may be a systematic way of doing this.
Yeah.
In this truncation, spin 2 is physically motivated, as you said.
Something that I don't completely understand is W infinity also contains a sub-algebra that is closed, finite. Maybe it's related to this consistency of this truncation.
There is a possibility that if you do a small momentum expansion, then you may have closure of a subalgebra.
Yeah, but I think if we go to, yeah, I want to talk to you actually about that. Yeah, and there is some old ideas of using non-commutative geometry.
Yes, that's exactly what it is. That's exactly what I'm talking about.
Yeah.
Yeah, so regarding that comment, so the algebra you had was SL2R, which is in some way related to the W infinity, but here you're considering only the global area preserving transformations, whereas the SL2R is the general diffeomorphism transformations. Yeah, so that's not completely clear.
So this is, if I forget this delta, it is SL2R.
So is it in some sense related to kind of preserving the volume of the Fermi surface, kind of like you have a area preserving transformation? So is that in some way?
Well, that is very interesting idea, but I don't know how to put that in formalism.
Partly think fraction where the Fermi surface picture suggests that you're equal to half.
Fermi surface is,
then you want the that in our state.
So I need to have incompressible state. So nu, so if I want to use this notion of the Fermi surface, then apparently I have to go to n divided by 2n plus 1 with large n, so that the magnetic field is small enough not to smear out all this Fermi surface. So one can argue that this calculation is valid only at large n. So for some miracle, some reason that also work, the q to the 4 also work in n equal to 1.
State you both the
for omega, so here you don't have a gap, so there is no pole, but there's a whole, yeah. And I think it's just q to the 4, but times some function of omega.
Actually had one.
It's a chiral. One can think about that as some wave that only has one circular polarization. It's a massive graviton, but only one chirality.
So if you take n to infinity, you have the half-filled nuclear half. What will happen to the magnetoroton dispersion then? It becomes gapless, or?
It becomes it goes down. Yeah, so the gap goes down roughly as 1 over n.
So at n infinity, it's gapless, and
this theory would
still goes like q4th?
I think it should go like q to the 4th, but the the coefficient in front of this q to the 4, some function of omega. And it's q to the 4 only if q is much less than omega divided by Vf.
Omega, what happens to omega?
Omega is, so this, there is a, the spectral density is just q to the 4 times some function. I don't know what power of omega.
Of time, let's move on and thank Sean for a very lovely talk.